Hey guys, hopefully you guys got through the first lesson okay. So today we're going to be talking about defining heat. Specifically, specific heat is what we're going to be working on. So we're going to be talking about the way heat is transferred and kind of what that means and how it can be measured in different situations. So we know that heat is related to energy, obviously, okay? So heat is going to be the energy transfer between objects because of a difference in their temperatures, okay? That is the heat. Transferring energy into substances causes the molecules to vibrate faster, and this energy is then transferred to the other surrounding molecules, okay? So that's pretty much basic chemistry, and I'm sure that most of you have taken chemistry or you probably remember that from ninth grade anyway. So objects are going to reach thermal equilibrium when both of those objects' molecules have equal kinetic energy. Okay, so when they've reached thermal equilibrium, you're going to have equal kinetic energy in both objects that are touching one another. Heat, just like work, is energy in motion and it's measured in joules. Okay, so remember, work was measured in joules and so is heat. So they're kind of right along the same pathway, and this will be important when we start talking about heat engines in the future. So if you look on this little diagram on the right-hand side, this table, we have different units for heat that we can be using or you might see, and then where they would be used at specifically. So we're going to be measuring heat in joules. You can also measure heat in calories or kilocalories. You have also a dietary calorie or a BTU. So sometimes you'll see BTUs, not really very often in the United States, but you'll see BTU on like air conditioning units or refrigeration units, different things like that. So you might see it sometimes. It's just another unit for heat. So joules is what we're going to use mostly. And if you look at the equivalent value, joules is equal to 1 kilograms times the acceleration. Okay, so joules is literally the acceleration of 1 kilogram of that substance. So it's talking about how fast these molecules are moving within the substance. We will also talk about calories and kilocalories and dietary calories pretty soon. We're going to do a lab coming up tomorrow or next class, but I just wanted to kind of point that out. So we do have different types of heat transfer. The first one I want to talk about is induction, and this one is not often talked about in heat transfer because it's relatively new. I mean, it's not super new, but it's not actually a transfer of heat necessarily, but people always ask about it with this unit. So induction is an electromagnetic field that heats the metals directly. It's super efficient. So in an induction, like an induction stove, you have a glass surface and there's a copper coil underneath of it. So electricity is run through that copper coil, which turns it into a magnetic field. And that magnetic field heats up, it transfers its energy into the iron particles in your cookware, and they begin to move around, which causes them to heat up. So it is only going to cause heat in an object that has a magnetic field, okay, so something with iron in it, and everything else would stay cool. You could literally put your hand on top of the stove and your hand would not get burned. It's safer because if let's say a towel accidentally gets on top of the stovetop, it's not going to catch on fire because it's not going to get heating up. It's not going to react to that. So that's what an induction oven is. So that's causing heat by transfer of electricity. So if we're talking about actual heat being transferred, we're going to have a couple different kinds here. We have convection. So that's going to be the transfer of energy through the movement of hot and cold matter. So in this example, you have like a boiling water here. Convection is happening because we know that hot air is going to rise and cold air would sink. Same thing happens with liquids. So here the convection naturally happens because as the molecules at the bottom heat up, they're going to rise because they are becoming less dense. They're moving around faster. They're coming further apart from one another. So they're going to rise to the top. And then once they're at the top, they'll cool down because they're further away from the heat source. So they're going to fall back down again. And then this just keeps happening. So that's your convection. Conduction is going to be the transfer of energy through touching molecules. Okay, so things that are like physically touching one another. Here, if you had the handle of your pan that you're or your pot that you're boiling water in. Most of the time you can feel that the handle is warming up. Okay, so hopefully it's not burning you. You have some kind of like rubber or plastic handle there, but The conduction is going to be just transferring between physically touching the two molecules. So the heat from the pan is touching the metal of the pan is touching the plastic of the handle, and it's transferring the heat through there. So the energy is just being transferred. It's kind of similar to convection, but there's no movement of it there. So you're just transferring it by touch. Radiation is going to be the transfer of energy through electromagnetic radiation, different from induction though. Okay, so radiation is going to be like the heat waves are radiating off of the object, like it's heating up the air around it, and then that in turn is heating up the object. Okay, so we have a hot coil down here that has been heated up, and then it is heating up the air and the surface, and then that is heating up whatever else is around. So radiation transfer of heat is the reason why things feel hot before you touch them. Okay, so that a pot of boiling water is going to be hot before touching the water, which hopefully you wouldn't do, but you can put your hand near it and feel the heat coming off of it. So heat and work are very directly related because the total energy is conserved in a system. So we've talked about potential energy, kinetic energy, and total mechanical energy in Unit 4, which is what's in this equation. When you add all this together, you should have equal to 0. Okay, so it's all conserved. So the total mechanical energy should account for the potential and kinetic energy. So kinetic energy of collisions can also be turned into sound energies. Mechanical energy can be turned into heat energy, just some examples of that. So some energy can also be absorbed internally by an object, but the sum of the changes in the potential kinetic and internal energy is going to be equal to 0. Okay, the sum of the changes, because you can't just create energy out of nowhere, and you can't just gain or lose energy out of nowhere. So it has to be accounted for somewhere, whether it's by sound, heat, internally absorbed, or whatnot. So we're going to go ahead and start into specific heat, which is the next section here. So specific heat is the energy required to change the temperature of a substance by 1 degree Celsius. Okay, everything is going to have its own unique specific heat, right? So the same energy is going to cause a different temperature change in equal masses of different substances. So water is one example here. So this pool here, the water is going to have a very high specific heat compared to the air. So the sun is shining down. And this is actually I forgot I even put this in here last year. This picture is of the community pool from when we used to live in Florida. That's funny. I forgot I did that. So anyway, the water has a higher specific heat than the air surrounding it. So the sun, let's say this is the Florida sun. So Florida sun is shining down. It's heating up the air much more quickly because the air has a low specific heat. Okay, so there's less energy is required to change the temperature of the air. Whereas water has a higher specific heat, so more energy is required to change that water at the same rate. So if you have the same amount of energy, the air will get hot before the water gets hot. Okay, so the formula for specific heat, you guys, I think, worked with this a little bit in physical science, and we did a little bit in chemistry. So you probably are familiar with this. So the formula for specific heat here is you're going to have the energy transferred is Q. Okay, that's going to be in joules. So it could be added or removed. So if it's added, it's positive. If you're removing energy, it's going to be negative. So that's that equal to the mass of the substance that is absorbing the heat. That's going to be in grams times the specific heat capacity, which is like a given here. So we are going to be using calories per grams times the temperature here, or joules per gram times the temperature. So kind of depends on what units you're using to begin with. So anyway, you have the specific heat capacity is going to be a given. It's going to be a constant for whatever type of substance you're using. All of that is going to be times the change in temperature. Okay, so keep in mind that your temperature needs to be in Celsius. The specific heat will be given to you, and then the mass needs to be in grams. Q is going to be in joules, or it could be in calories, depending on what you're talking about. So make sure that your values for the energy transferred and the specific heat match. So if you're measuring this in joules, make sure you use the specific heat value for joules, okay, not the one for calories. This can also be rearranged here to find the specific heat capacity if you know how much energy has been transferred in the mass and the temperature change. So that it can be used for calorimetry, basically. So calorimetry is going to be to measure specific heat, you would need the mass, temperature change, and energy transferred as heat. So that is calorimetry. It's the process used to measure the heat that's being transferred. So you can figure this out using little devices called calorimeters, and this can be like homemade. And this is what we're going to do next class. So what we can do is figure out the actual specific heat or the actual amount of heat being transferred in a substance by burning it and figuring out the change in the water that's inside of this cup or the soda can. So basically what we'd have here is we'd have a measured amount of water here, so we would know the mass of the substance that's being changed. We have the thermometer inside of the water. We're going to have the food on top of a little holder here, and we're going to light the food on fire. And what we're going to be measuring is the change in temperature of that water, which we can then use to determine some of these other values. So we're going to know the change in temperature of the water. We know the specific heat of water. We know the mass of the water. So we're going to be able to figure out what the transfer of energy was, which we can measure in joules or calories. So we're going to use that to figure out how many calories are in these little pieces of food that we're going to be burning. So one example here, you're able to raise the temperature of 50 grams of water from 21.8 degrees Celsius to 27.1 degrees Celsius. How much heat was gained in calories by the water? Okay. So what we're given, we know the mass of the water is going to be 50 grams. We know that the specific heat of water is going to be 1. And we know the temperature change is going to be 5.3 degrees Celsius. So we're trying to solve for the heat transferred, okay, how much heat was gained by the water, which is Q. So we're just going to substitute in our known values into this formula and solve for it. So we'll have 50 grams times 1 times 5.3 is going to give you 265 calories. The very last thing we're going to talk about today is latent heat. It's related to specific heat and calorimetry a little bit, but it's more talking about how energy is transferred and kind of what's happening in between your phases. Okay, so latent heat is going to be the energy that's transferred during a phase change. So as maybe you have a solid that is melting into a liquid. What is the energy that's transferred during that transition? So energy added to a solution to cause a solid to turn into a liquid is going to be the heat of fusion, and the energy needed to change a liquid into a gas is the heat of vaporization. So if you look at this heating curve, the temperature is constant while the phase is changing, and the phases will not change until the certain energy requirements are met. Okay, so the temperature is constant while the phase is actually changing. So if you're looking here at, let's see. All right, so let's say we have a solid to a liquid, this portion right here. So as the solid is melting, as it's turning into a liquid, the temperature is constant. The temperature will not change until the entire substance has turned into a liquid. Once it has turned into a liquid, then the temperature can increase until it gets enough energy to change phase again. So now that it has enough energy to change phase again into evaporation, it's going to remain at the same temperature until it gets enough energy to turn into a gas. So that's your latent heat. So we will talk about heating curves a little bit more, but that is the end of today's notes. So you guys do have an assignment. It's just a few specific heat questions, and then there's also an escape room to complete. So please let me know if you do have any questions, and I will talk to you guys next time. I hope you have a great day.